Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to look at pointers using the C++ programming language. This is basically a review of Chapter 9 of the Gaddis book that we use for our coursework here at the college. So what I have set up for here is I have my PowerPoint, I have my Visual Studio ready to go. So let's take a look at a few of these things here. So what is a pointer? What is a variable? I mean, these are things that are very fundamental to understanding computer science as a whole. So a variable is simply a memory address in your computer, in your RAM, where you can access data and treat it, and then basically get information and put information to it. We would call it a name like X or Y or total or sum, but to the computer itself, it doesn't care. It's just a storage place where basically information can be stored. So to get to an piece of information like that, I use the address of operator, and that's where the whole idea of references, Chapter 6 idea comes from. When it comes to pass by value versus pass by reference, that little ampersand means a lot here. Int x equals 99, and so now there's a big difference between printing out the address is, or I use that little ampersand, and I say, okay, get me the address of x. Tell me where x is in memory. Oh, and I need to use colon, and then, so something like this, get me the address of, and then what about the value? And that's just like everything we've ever done before, where you just go ahead and set up and just plain old x. So in this case, of course, the 99 will print out when it comes to what the value is, but you can see here, it's 94C, and then when I run this program again, it's a completely different memory address. Because every time I run my program, the operating system is giving me a different block of memory to use, and because of that, as you can imagine, when you're talking about 2, 4, 8, 16, 32 gigabytes of RAM, how much RAM you're giving, and you're just spreading everything across, you're never going to end up in the same place twice, or very rarely will you end up in the same place twice. So that's where this is coming from. I can get the memory address of something by using the ampersand. And so if I take that one step, I can go one step further and start actually using that memory address in what we call a pointer. So a pointer variable is a variable. It's a variable like anything else. And I could say int pointer, the star, doesn't mean multiply in this case, y equals address of x. That's the syntax that we start with here. I like to put the space here. It's just the way I do things. And so it's just called a pointer, and it's a variable that holds a memory address. It's because what is stored in any variable is a number. And in this case, this number is basically a reference, right? That's what the address of operator means. Give me a reference to another memory address. And so because the pointer variable holds another memory address, it points to the data in which we're discussing. Here is a similar example using an Excel worksheet. And so if we were going to try to mimic what is going on an Excel worksheet of what a pointer is, you would see here that somewhere in my RAM, somewhere in my spreadsheet, think of it like that, right? It's just a bunch of cells, a bunch of pieces of data that can be stored somewhere in the spreadsheet. So X is just stored somewhere, and every time I run my program, it would be somewhere else. But right now, it is right there. Oh, I can almost point there. I'm never going to be a there you go, x99, never going to be a weatherman. So you can see that the x value is stored as 99, as we see up here. And then now that I'm using int pointer y, instead of holding a number, it's still holding a number, but in this case it's holding D5 because that's where the data is stored. So it points to the data because it doesn't hold the data itself, but it tells me where I can go to get the data that I'm discussing. And so we've already kind of worked with pointers, and I kind of discussed this previously when we talked about arrays, is that especially when you're passing arrays around, the square brackets and the way things work, the syntax would work and the code would work identical if I removed those from the parameters in the function call and replaced them with a pointer. because even though we feel like we're passing an array by value, which would mean we're copying the array around, the reality is we're actually just passing the pointer. So the reality is we're actually passing a reference or a memory address instead of a value, because it would be wasteful to copy the entire array just to use it on the back end. And so we have to watch out for that when we start using the standard template library. If we forget that little ampersand and send things by value, we're going to make copies of all the data structures that we're going to be discussing here. And so, so that's where we're going with this. So again here, show values. If we, just to say here, we're sending a memory address. We're sending a pointer to array. And if you get rid of this and replace it with the star, the code would work identical, which is interesting, right? So I don't understand sometimes why to have different syntaxes that do the same exact detail, unless there's something under the hood that if I use the different syntax, I get different behavior. The compiler will compile something slightly differently. So let's see here. So here is something that basically is the idea of references and pointers are not identical, but they're close. And so we can say here that when we passed things by reference in chapter 6, we were essentially fulfilling the same behavior of pointers, because we're passing a memory address along to this getOrder function. And notice, even though it's a void function, by getting the input from the user, I'm modifying an actual variable sitting under here. Even though it's called donuts here, if I use this call to call the function, I'm actually modifying the jelly donuts variable here on the side that's calling the function. And so again, what's being passed along is not the 99, a copy, as if it were being passed by value. We're basically passing the D5, the memory address of where to go to get or to store the information in which we're going to be using inside of the function. So let's see. So that means that at the end of the day here, I have two completely different ways to access the data. There's one piece of data, but two ways to access it. And so I can access it directly through X or indirectly through Y. And so what this says is pointer variables are another way to address memory and to work with pieces of data. So I kind of call these anonymous variables, if you want to think of it that way, where I can, like these guys, normal variables are kind of hard coded into my memory. But when I'm using pointers, I can jump around. I have free reign to go from memory address to memory address and kind of do whatever I want, but I'm hard coded, I'm constrained here with the normal variables. And so this is about as low level as you can get, because you're dealing with basically raw memory. So pointers are definitely more low level than things that you're used to using. And that's why it's challenging, and it was challenging for me as well until one day it just finally clicked. And so, it's very low level, right above, the assembly language level is where, raw addressing is when it comes to memory. And so, you got to get used to that. And then because of this power that we're given, that we can just jump around and do what we want, we have to be good. We have to understand what we're doing. We are responsible for finding the memory addresses we want to use and making sure that we correctly use it so we don't ruin the whole process and completely bork our program as we're trying to do this. So again, this is what my syntax is, the way you see it here. Visual Studio already tried to modify it and make it to that. It's the same deal. It doesn't necessarily matter how you do it. They say the wrong way, LOL here, is that this way. I do not like that way. I either like this way or this way, but it doesn't much matter. The tokens, the tokenizer of the compiler can figure it out no matter what. And so now you can see here's their example as what I was showing here a minute ago. They have their num, we're using X, they're using num, and we have this, which is pointing to the memory address where the actual value is stored. And again, this is an Excel worksheet, so D5 would be the answer, but the reality is, as you saw previously, it would be a 32-bit value that's being stored in that location. Okay, so another thing you can do is basically have a pointer that's looking at null, which is 0. But in this case, C++ since 2011 has this idea of null pointer. So int pointer x equals null pointer. And let me run this program and see what happens when I run it. Oops, I don't. Oh, I have x twice, and I'm terrible at naming things when I'm talking. But you can see here I mouse over, and the z value is actually stored as a 0. So null pointer resolves down to an actual physical 0 value, but you get more checks and balances when you use an actual keyword like null pointer, as opposed to null, all uppercase null, or 0 when you're doing this kind of stuff. And what that means is that it's not pointing to anything. But what it also means is, and we haven't accessed any of this information, if I try to access z, and basically so, hey, go to z and put a value inside of there, or go to z, get me a value from there, this thing is going to crash because nothing is stored at null pointer, and it's an access violation because obviously memory location 0 is not part of my program. It's outside the walled garden in which I was given. So the operating system says, stop this right now, and we'll show this in a minute once we get to discussing how to actually access all of these things. So here we go. So they're doing exactly the same stuff we were doing earlier, but now, let's see. Yep, now we can play around with actually changing and using both pointers and regular variables. Okay, so in the little break I had, I've set everything up so that I'm setting up an x, a y, and a z, and I'm trying to print out the address of both of these, of all three of these, and their values. So right now, this is what I get if I print out all of this and their values, and this is kind of weird, right? So I get, here's a memory address, here's its value, right? Here's a memory address, here's its value. Here's a memory address, here's its value. So now this is interesting, right? So x is a memory address, fair enough. 99 is its true value, right? That's stored at that memory address. That's a normal variable. So now when I'm doing y, which is storing address of x, of course it has a completely different memory address. It just happens to be very close to this other one, but its value is the address of x. And you can see that here, right? You can see that this is actually the address of x. And then the next one is just one step over from that, which is pretty cool. That's because of the way the stack is actually doing all the hard work. So every variable is in a different memory location, but what's stored there is completely different. And in this case, this isn't 0. This is a address 0. That's why it's printing out 8 zeros, because it's a memory address of z. And it's weird. But what if I tried to change this up and say, okay, how do I access this correctly? Because how would I know in the y case or the z case? How would I be able to get to this information? I'm surprised the y, because it's a pointer. So, again, it's been a while since that I've been doing assembly language for the last week or so. So just getting back in the swing of things here. So if this is a pointer, this is a pointer, this is actually giving me memory addresses. But I'm like, how about you give me values? And that's where this idea of the star comes from. It's a dereference operator, which basically means that if I have a pointer, which is a memory address, it says, hey, I know it's a memory address, go there for me and get the value stored there. So it takes one extra level of what we call indirection to go from a pointer to get to the true memory address to get the true value and bring it back. So coming back to our idea here, if I was using this and saying, okay, hey, y, I know you're storing a pointer, I know you're storing a memory address, can you go to whatever's stored inside of you, and in this case D5, and you go over here, and then you get the 99 and bring it back. And the 99 is what will be printed out here, in this case, this time around. So instead of printing a memory address, now 99 is printed in both places. And so the reason I held back on this is what will happen if I do star z. And what happens is I get a crash. Read access violation, z was null pointer. And again, what happened was, this is when z is pointing to a null pointer, it's pointing at memory address 0. And if I try to go, hey, why don't I go to memory address 0 and try to access the data stored there, memory location 0 is not part of my program. It is, it's outside of my walled garden, and the operating system says, nope, not going to happen. And so, you can already tell here it's giving you a big warning. You're trying to dereference a null pointer. And so this is a big deal. This would happen to us a lot on the job site. The program would crash on us, and then you'd spend 15 minutes debugging the thing to find out, lo and behold, you had a null pointer staring at you here. So I can't dereference a null pointer. So you have to watch out. You would probably have to put an if statement around this so that you don't crash the system. If z does not equal null pointer, then print everything out. It won't print this thing out, but at least it won't crash, right? It's printing the address of z but not the value because z is a null pointer. And so if I change this just like before here to address of x, of course all three of these things now point to 99, and it actually prints out because the z pointer is not pointing to null. So in this case, what we're dealing with here is another thing somewhere in memory. In this case, it's actually next door, but not necessarily has to be every time. Okay, you're saved to this PC, that's great. And so x is the true value, z is storing d5, y is storing d5 as well. So now coming around to it, how do I change the values? And I guess they're not even going to discuss this just yet, but I'm saying if I change x here, if I change x after I printed out 99 and say, okay, it's 32 now, you will see that, okay, even though it printed out 99, y is 32, even though x is the value that has been modified, because y is pointing to the true data stored under the hood, it gets affected too, and same with z. So the data is only stored in one place, but everybody else can access that data. And so the same thing goes here if I set x is 32, or if I say star y equals 52, which, well, I guess it hasn't been defined yet. If I go ahead and change this and run my program, you can see now everything has been modified to 52 because now indirectly through y, I've gone ahead and gone in and changed the original value of 99 into 52. And the same would apply for z, since everybody's looking at the same piece of information, and since it's only stored in one place, you change one, it changes everybody else indirectly. Nobody gets alerted to this, but the value has been kind of swooped out and changed under the hood. So I've gone ahead here and set up an array. So there's a relationship between arrays and pointers as we discussed. So just to, this is the program, this is what prints out. So going back to previous lectures, if I try to print out vals, if this was Python, it would show me the entire tuple or list or whatever I've got going on under the hood. But because this is C++, what this prints out is the memory address. It prints out the pointer. Because again, even though this is syntax like an array, it's essentially a pointer. This could, so just the syntax could be a little different, and we could get to the same result here. And so, so val 0, this is how we're used to array notations, right? When it comes to the way things work out. So this will print out the first value, and that's why it prints out the 1. Oops, that's not it. Come on, close out. Here we go. There we go. So it prints out the 1 because that's what's stored at the 0th element. And if I do 2, of course, it'll print out 3. Just got to drag it over to make it work. So that's how so displaying things, that's one way to go about doing it. And so you can see here what I can also do is do this. I can do star vals, take vals, which is a pointer to the first element, dereference it, and print out what's there. It'll print 1. And so that's kind of cool. And so what that literally means is that I can access things 2 separate ways. I could say val sub 0. 0 is a little weird. I could do it like that, or I can actually do this, vals plus 0. So this will print the same value twice because both of these are get me syntactically to the same memory address. And so just to say that if you can do things that way, then I can go and actually reverse them. And so now 3 times over it prints the same value. And now, impress all of your friends in computer science, that means I can do this. If someone asks you this at an interview, you're going to get the job. Not many people know this. You can actually access things this way. I can say, give me a number, and then in square brackets put the array. Because under the hood, syntactically, the tokenizer, when it puts it all together, turns it into one of these things where it's just adding the two values together. So if I want element 4, which is the 5, I could put 4 in square bracket vals. Isn't that weird, right? And it does print the 5 because, again, it syntactically works its way back to the exact same memory address. So interesting, fun stuff, right? So what more is there? So, yep, so you're seeing here star val plus, because what is this saying at the end of the day? What is any of this saying is that says, get me the pointer to val, so get me that memory address, move over however many elements, and then dereference whatever's at that memory address. So if I wanted to say vals 2, for all of these cases, it says, go to val, wherever val starts, which is the first element, shift over 2 elements, and then that's what we're going to be playing with. That's the memory address I want to talk about. And in this case, now it'll print out 3s instead of the 1s prior, because we've shifted over accordingly and made it all work. And you have to use the parentheses because of the way the order of operations work in these cases here. So this is just to show, so you can do things like I was showing you. I went into a little more nerdy detail because I think it's interesting from a computer science standpoint about how there's so many different ways to access certain memory addresses here. So, and no bounds checks are performed. You never know if this is going to crash. Let's see if it crashes. Nope, not this time. Even though what comes out of this is complete garbage. Like, oh, it just printed out a 1 by happenstance. Well, what if I just put a huge number in here? Nope, nothing yet, but the value is garbage, but I haven't crashed it. See, that's the thing with undefined behavior, right? There it goes. I finally blown this thing out far enough where the operating system finally tells me that's no good, and I have to stop because I'm accessing something I'm not supposed to be accessing. Okay, so pointer arithmetic. I can actually go ahead and, with pointers, increment and decrement them and do plus equals and minus equals. And what that just means is I'm taking a memory address and I'm trying to shift over one element. Just like I'm taking this, I'm saying go over plus 1, and let me bring this back. Let's shift this back. I'm trying to say go to vals and shift myself over 1. What I can do is do something like this, where I can say, give me an int pointer z equals address of vals. Okay, so that gets me the first element, or an address to the first element. Oh, is that not going to work? Okay, syntax is fun sometimes. How about just vals? There we go. And so this proves to you now, since this let me just prove it compiles and runs, not runs, but at least compiles for you. And so this says that the pointer and the square brackets for an array are interchangeable, or at least in this case, it's interchangeable. And so what I can do here is I can go ahead and print out star z, and that should print a 1, correct? And it does, because it's the first element. But now what I can do is I can go plus plus z, and then print out again. And so this will take the 1 out of here. Then it moves, z is pointing to the first element, but line 9 here says, why don't you move over 1 element? And then it says, now print out what you're pointing at. So now this will print the 2. So this is a big deal when it comes to pointers, because we're going to be using iterators, which are just fancy, super smart pointers. When we get into using vectors and lists and sets and maps and all sorts of things, we're going to be using these things nonstop. It's because there's no other way to access the data stored in these collections. So we're going to have to understand how incrementing and decrementing pointers and or iterators work. And so if you see where we're going with this thing, I could set this thing up and say const int size equals 5. Let's start doing this thing the more correct way. I say, okay, set up a 5-element array, and let me get rid of this thing here and say int z equals val, and now what I can do is say for, oops, I took away the wrong one, here we go. So for int I equals 0, I is less than size, oops, plus I, print out whatever z is pointing to, and then increment it. And then with an end line, let me just put a space in here instead so I can print this all out on one line. And now the fun of it is, here is another alternate way of going ahead and printing out all the elements of an array. Because this is Z is pointing to the first element, it prints it, increments the pointer to element 2, comes around, and then prints out what it's pointing to, the 2, increments it, and so forth and so on, until I've done this size time. So then what's weird about it here is, okay, we've got the job done, but say just as a side effect of all of this, when I'm done with the loop, Z is pointing to an element that doesn't exist inside of this array, because it started pointing here and then it shifted over 5 total times. 1, 2, 3, 4, 5. If I try to dereference this, if I say, okay, when I'm done, I come out of here, I try this, best case garbage data, worst case I've crashed my program because I'm out now, because I'm trying to reference memory that is not part of my array. And so undefined behavior, and what happens, you can see here it prints garbage because I'm not supposed to be there, but I haven't ruined enough so the operating system says, hey buddy, what are you trying to do? You got to stop this. I will not allow this to happen. Okay, so initializing pointers, we've already gone ahead and talked about initializing pointers here. So there's not much more to say about that. And so we can have 10 things pointing to the same memory address. Sometimes we do with video games and stuff like that. Part of the reason why we use pointers is so that we don't have to have the same information in our program in multiple places. Like for a video game, if I can have a repository where every object in my game is stored, then I can ask for access to this later on and go, hey, can I get the ball for the paddle game? For a Pong game, and then I can ask for a pointer, I'll get that pointer, and I can access the data without having to make a second copy of this, because especially for video game stuff, one object can hold hundreds, tens or 20s, or maybe even up to 100 different variables or more, depending on the complexity, and you do not want to be copying 400, 800, 1,000 bytes every time you just want to access something. When I can get a pointer, I can get a memory address which stores 4 bytes, and then I can go in and look or modify the data sitting under the hood. And so this is where things also get weird here, is comparing pointers. So let's talk about that. So there's a huge difference between these two if statements. And so if I compare, let's presume PTR1, PTR2 are pointers, and they have to be to the same data type. So like I have to have int pointer, if I have int pointer Z and int pointer W, and if I do a test, I say if Z equals W, and again, remember it's a double equals instead of a single equals. And so I can do something like this, and this will test the memory addresses. And don't worry, the error is just because I haven't initialized things. But W gets tested against Z. If this was a character pointer versus an int pointer, this is now a compiler error because the two pointers have to point to the same data type. And if I want to change that, I would have to do some kind of casting to cast like a dynamic cast or something to take something and cast it to another data type. So yeah, you have to watch out for that. But again, this tests the memory locations to basically see if I'm pointing to the same memory location. This goes ahead and checks to see if at those two memory locations, if the values stored are the same. Huge difference. So watch out for that as you move forward. So you have huge difference again between checking to see if the pointers are pointing to the same memory address, and or what the two things are pointing to are different values. So in a way, if these were pointing to the same memory address, both of these statements would be true. Because if these are equal and they're pointing to the same memory address, then their contents would be exactly the same, identical. So the test for equality would come through true. But if they're not equal, if they're pointing to different memory addresses, there still is a chance that what's stored in those two places are the same value, but it's probably less likely, of course, because anything could be stored in these two different memory locations. Okay, so coming back, keep on going here. We've already talked about pass by value. We've already talked about pass by reference. And so we can just write a little function here to play around with this and just understand how pass by pointer works, because that's the third way we can pass something along inside of a function. So I can say, give me, here's a value type, here's an int reference type, and here is a pointer type. And so what I'm going to do here is just set everything up very quickly, print out the value, something like this here, print out value, print out reference, print out pointer. And you will notice immediately a compiler error here. Come on. It won't do it. I keep forgetting that it's not a compiler error. If you try to print a pointer, it will just do the wrong stuff. And isn't that fun? No warning. There's no warning there, is there? Nope, just the stupid thing with the W that I can get rid of. Stupid stuff here. So, yep, no compiler warning, no error about anything, that this is just going to print the memory address. So I have to dereference if I wanted to point to, or if I wanted to print the value that's stored at that memory address. And so now what if I change the value? What if I change the reference? And what if I change the pointer? And then print everything out another time. Here, let me put an end line here, just to go with it here. Okay. So as you can imagine, under the hood here, when I call this function, when I pass values in, it'll print whatever value got passed along. It'll change the values, and then in each case, it'll print that changed value. But coming back to it again, what happens over here to the values? What gets copied? What doesn't? So I can say int value equals 7 int reference. I can actually do this. Reference equals 9. And the syntax is identical. But then if I do int pointer, then oh goodness, I have to point to something. So let me just set up another variable here, and I go just because of the way things have to work. And so equals address of D, because a pointer, unless we dynamically allocate memory, which we have not yet done, and we will be doing plenty of in this course, unless what did I do wrong here? To non-run, it must be an null value. Oh, I guess the reference is the same deal. Int E equals 10 equals E, int reference, there we go. It's been a while again, pointers and references and that sort of stuff, my apologies. And so int D equals 8, and then so now the address of D. So all these values, crazy stuff, right? 7 is a regular variable, E is a regular variable, D is a regular variable, and to be able to have a reference to something, I have to be pointing to a memory address. So I can't have a hard-coded value because it's not a memory address, it's a literal value. That's why I had to go back and fix this up and say, okay, point to E, or I want a reference, and I'm referencing E. And so this is basically the same deal. The pointer and the reference needs to go to a memory address, but again, the syntax is completely different here. So it's interesting. I think it's pretty cool. Okay, so now coming back to this, if so printing everything out, so it'll do stuff. So it'll print here, these three go in here after I call the function. I'll call function, and I'll say value, reference, pointer. So I can pass the three things along and then print out on the back end. It's a lot of prints, a lot of print statements here. So let's see what we've got when we actually try to run this program. Oops. And you can see, let me just real fast here, 7, 10, 8, 7, 10, 8, 1, 2, 3, 7, 2, 3. So things have been moving around a little bit. So let's check out, interestingly enough, right? Let's check out and go line for line through this. Okay, so value is 10. Here, hold on, let me pull up Excel here. Okay, so go ahead and set up Excel here, and you can see these variables, all the pointers and everything, all the references and everything they're all kind of randomly assorted inside of memory here. Value gets set to 7, E gets set to 10, reference gets set to the address of E, D is set to 8, and pointer is set to the address of D. So that's what goes on here. So if I print out value, it'll print out 7. And then if I print out reference, it'll print out whatever's stored at the memory address of E. Even though this is a memory address, the syntax is the same as a value type. So it goes to E and we'll print out the 10. And then when it goes to pointer, it says, okay, this time around, yeah, the same thing, go to D, dereference, and give me the 8 and print the 8. So right now, if I'm running the program, oops, did it not print? Okay, yep, there we go. It prints 7, 10, and 8 like I was discussing here a second ago. So, okay, oh yeah, we can kind of do everything all at one time here. So now, if I call the function and I pass the information along, what is happening? So what's cool about this here, because I'm passing value by value, what's basically happening is on the stack here, I can just call it's, just call, I'll say copy of value in this case, and I can just bold it up. And what's getting passed along is a 7, a copy of whatever's in the value right now. So that's what's going on. And so we have a copy of value passed along, but when it comes to the other two types, when I pass by reference and I pass by pointers, instead of going to the old copy machine and passing along a copy, I'm actually using the real memory addresses. I'm really using the address of E and the address of D to get the job done. And so now when I go into this with F11, I can keep going through and I go, okay, now when I print, of course, everything should print the same. I haven't modified any values. So the same 3 values should pop out. And there it goes, 7, 10, 8 a second time. And now when I change the values, I'm changing value to 1, which means this is now a 1. But now value is this value, the copy of. It is not this one here that is sitting on the main side. This is a copy of this sitting in here in this function. But when I go to change reference, reference says go to memory location E and change that. And so I did. It's the real data, not a copy. And the same goes for pointer. Go to address of D and change its value stored there. So now when I print everything out, when I go to print value, which is the copy stored in my function, it prints the 1. And there goes the 1. And when I print the reference, it prints the 2, which is pointing here. And then when I go to pointer, it points to the 3. And so my function is complete, so I'm done with it. F10 one more time. But now what happens is everything falls off the call stack, and this copy goes away. Delete it out. It essentially no longer exists, no borders. It's as if nothing ever happened. And so now when I come back on this end and I go, okay, let's print all what we've got, now coming back, value is now the value that was originally stored in the main. It's not the copy. And so now it actually prints the 7. And then now when it goes to print the reference, it prints the 2 because that's the value stored in location E. And when it goes to print D or pointer, it'll print the number 3 because that's what was stored at the memory location pointed to by the pointer. So that's why pass by value and pass by reference and pass by pointer, like 2.5 ways to do the same stuff. That's why they're so different. And until you've done this a few times, it's like, what does this matter? It's a huge difference. And especially when we move into the standard template library, and if we accidentally pass something by value, a huge data type like a vector with 1,000 elements, we're copying the whole vector. And then on top of it, if I'm trying to modify it, it's modifying the copy, not the data I really want to modify. So we're going to have to pass references and pointers along to a lot of different things to make sure that we're scoping correctly and passing and changing data in the places we're expecting to change. And it takes a little getting used to, and sometimes a lot of getting used to make this stuff work out. So that's where this is coming from. Functions as pointers as function parameters, they are swapping information and stuff like that. Just, like in this case, they're just showing you this. Of course, under the hood, I would use the true standard template library swap function to do that instead of writing my own, rolling my own. And so consts, this is the fun part here. I can put const, like I said, I can break everything by putting the word const in front of everything here, especially for the value types and the reference types, right? You see that this breaks down because I said that this is const. But what's interesting about pointers is, what happens if I put the word const here? Okay, this breaks. just like before. But what if I go ahead and I put a const after this? And now the fun is this actually works. This actually compiles. And so this would actually run just like we showed before here. There it goes. It runs my program. I don't know why it doesn't show me what's going on. But what's interesting is there's two separate ways I can use const on a pointer. And so one way is that I can't modify the data stored at the memory address the pointer is pointing to, just like I can't change the values of the value or the reference type. So that's why this breaks down, is because I can't change whatever pointer is pointing to the value 3. But on this end, right here, if I do this, this means that I'm fully in my rights to go and change the data stored at that memory location. But in this case, I can't actually change what pointer is pointing to. Huge difference. Now, see, this is perfectly legit here with const here, but this is not, because I'm not allowed to change what pointer is actually pointing to. So again, so if I get rid of this, I can do both. And if I put this back, I can do this. And if I put const in both places, I can do neither. And so there's 4 different ways that we can apply constness to a pointer. Either no const at all const in both cases, or either or. So it's tricky. And how often do we use this cult of constness? Not quite too often. Depends on the company and how you feel about it, because const can overrule your life. And what's interesting, because const correctness is what it's called in C++, const, pass const, do this, const reference, const this, const that. And then when you look at a programming language like Python, there's not even a keyword called const, because they realize that const is a curse more than anything. And so it was a great idea at the time. It turns out in practice, over time, it's not truly a great best practice. Depending on your major, or depending on what class you are taking, you can either skip this section or you have to go through with it. So if you are a computer science major taking CIS 2541, this is required for you, and especially for CIS 2542 as well. But if you're taking like engineering C++ or something like that, like a 3-credit version of this course, you should watch this, but you don't have to understand 100% of what's going on. So dynamic memory allocation. So there's 2 keywords basically in programming when it comes to when variables and when memory addresses get allocated in memory. And the first one is called static. Everything we've been doing is static. And what static means is at compile time, the compiler figures out how much memory we need for all the variables and all the extra junk that goes on, and it sets all of it up. So when the program runs, there's a very specific hard-coded section of variables in there doing their job. And so that's typically normal. We never have to worry about that, because since the compiler sets it all up, the compiler automatically will remove all of that information in the certain cases it needs to. Same with scoping rules, when you create and destroy variables and that sort of thing. The compiler works all of that out for us. But when we're doing things what we call at runtime, and we're saying like, I need more memory at runtime than I anticipated, that's when I start taking control of memory. And so with that comes great responsibility. And so that's called dynamic memory allocation, is that while the program is running, I ask for more information, more data. And so it's a little bit different. It's much different, and we have to be very careful with what we're doing here. So we can dynamically allocate memory. And basically you're asking the operating system to help you out. You can't just go, like you said, in the old days, you could just go in and just blow out whatever you wanted to. In the modern day, you have to ask for permission. So like this, in this case, if I wanted I just want to create an integer out of thin air, I would say int pointer x equals new int, and I can put in parentheses the value I want to store there. And so that keyword new, if you're coming from Java or C#, you've seen new every time. If you watch Doctor Who Season 2, Episode 1, New York. You've seen new in certain ways here. And so the new operator will return a pointer to the memory address that the operating system has allowed me to use. And so you can't do it otherwise. You can't just say int. You can never You can never set a pointer equal to a hard-coded value. It's just not allowed. I have to set it up to a piece of memory, a memory address. And that's how things go here. But once I've done that, I could treat everything just like I always have here. I could print out the value of x, and it will, I forgot because it's a pointer, it gives me the memory address. I forget that every single time. And so I need to I need to dereference that, so it'll give me the 87. And so there we go. So I newed up memory, and I've gone along with it. So basically, I'm creating memory out of thin air. And as long as the operating system, as long as your computer has memory, it'll do it. It'll give me. And what's interesting here is, if you want to see, or I'll just use a while loop, while true, give me memory. And I'm not going to print the thing out every time. Let me just comment this out for a second. You're like, oh, this is fun. Like maybe you see this, maybe you're not. Like this is where we have to start understanding the consequences of our actions. And so if I run this program, it's running. I don't know exactly how long it's going to take. I'm on my machine. I just recently upgraded my processor because my motherboard went to crap over winter break. There we go. So we have an unhandled exception, and that's what's happening is because I keep asking the operating system for memory, it keeps obliging, but I am never giving it back. So as long as this program is running, I keep begging the operating system more, and eventually it's got to run out. Every computer is, no matter what, right, is going to eventually run out of memory if you keep asking for it, because there's only a finite amount of it. So we have to be careful. Like I said, we never have to worry about this when we use normal variables and even references to things. Everything kind of works out. The compiler handles everything. But what we have here is what's called a memory leak. And so what's happening is we're asking for memory and we're never giving it back. And what happens is when I hit this closing curly brace, X dies, but the memory that I borrowed from the operating system doesn't. So the scoping rules are completely different for this kind of thing than for something else. So let's see, we'll see here. This is, and you can access things any way like you normally did once you've newed it up. The hard part is getting the new to work. And after that, it's the same as every pointer we've been talking about for the last 45 minutes or so as part of this lecture. And we just proved that the program will terminate. We'll get an exception thrown if there's not memory because of the memory leak that's occurred. And so what happens is, to give back the memory, we delete X. We new it up and we delete, and now this program will run forever because it's a terrible churning of memory, but it works because every moment it's like, give me memory, and then I'm like, oh, I'm done. Here you go, take it back. So there's a net zero gain. So instead of just take, it's a give and take relationship, and it all equals out. So everything works out. So it will run forever, and it's an infinite loop essentially. And I'm just borrowing 4 bytes of memory at a time and giving it back. So we'll see as we progress further into this. It's never as easy as you see for larger programs, because the general rule is for every new you have to have a delete, but where you do the new and where you have the delete can be in completely different parts, completely different sections of your code base. And so when I worked in the slot machine industry, nobody warned me about this. My first project through is you get the worst bug report from the testers ever, and it's like talking to your mom about why your computer is broken or why her computer broke. It just broke, and the bug would come in and it would say there's a memory leak, and you're like, oh my god, I didn't write any of this code for anything that's running under the hood. But what the error message would say, how would you recreate this? You would just let the game run for 54 days or something, or just an extremely long amount of time, and then one moment, 54 days in the future, the program would crash, and now it's my job to figure out how to fix that error. And so, as you could imagine, with a system that you are just brand new to, that has been working for 20 years, and this is probably something that's inherent in the system. It might even be a driver issue. It might not even be your fault. Nobody seems to know how to help you out. It's the worst kind of bug to fix, because how do you find out if the news and deletes over 54 days don't match up directly? Because again, even if it's off by one single byte over the course of time, you will completely chug up and completely ruin all your memory, and eventually you will run out of memory and you can't do anything more with it. So you got to watch out. And what's interesting here, I can create an array. This is just an integer pointer, but I can set up an array. And I can say, give me 10 elements. And then I think I could initialize it. C++ is fun now that they've upgraded since 2011. Wasn't so much fun back in the day. It was like, I wish they would do this, and then they obliged, which is awesome. So I can actually set up an array, but notice it's a pointer. I don't know, can I set it up like this? Nope. New initialization, blah, 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 expected for aggregate object. Oh my God, whatever that means. Let's make it a pointer again, and everything's going to work out just fine, right? So there's my build. Oops, of course I want to stop debugging. And yes, everything is fine. And I can access this array like anything else. I mean, even though it's a pointer, I can do a cout of x at the 5 location. Because again, the syntax is different, but this is saying go to the first byte of the contiguous block of memory where x is stored, move over 5 elements, and print out whatever is stored there. And let me just, so it'll print 6, right? Oh God, the mark of the devils. I didn't even, all these things I'm not trying to do. Okay, but it's printing out 6, 6, 6, 6, 6, 6, 6, 6, 6, and it's never deleting anything. So actually this will crash much faster. Instead of asking for memory 10 bytes at a time, or 4 bytes at a time, it's asking for 40, but it's actually going faster, taking up memory, but it's slower printing it out. So I guess it's a wash as to how much time it would take. But what you got to watch out for when you're newing up an array is when you delete, you have to put the square brackets into the delete. Because otherwise, you'll have another memory leak. And the thing tried to warn me here. That was pretty nice. But this thing is trying to warn me. Come on, warn me like you did before. Come on, come on. Oh, man. It was warning me a minute ago. 2019 is amazing. Sometimes, occasionally, it was trying to tell me, because it knew that this thing was an int pointer, that I wasn't. Yep, there it is. X is allocated with array new, but deleted with scalar delete. So it's 2019 here is trying to tell me. I wish it would just tell me what is the solution. Just you got to do that. You got to put the square brackets in here to tell it to give back the entire array to the operating system, as opposed to just the pointer itself, 4 bytes of memory. So again, the hard part is just getting these things up and going. And so you got to watch out here, like I said, again, in the cases, at least getting going here, at least while we get used to this kind of idea. If you knew everything up, just make sure you delete it out. Once the scoping falls away, delete it as the last thing you do. So new it up here, do stuff with it, delete it, and you're good to go. Okay, and then coming back here, pointers to functions. Let's talk about that. I believe this is the last item, the last major item. Oh, there's something else here. Yeah, we won't talk about smart pointers today. We might save that for a future lecture. So how would I return pointers from functions? So I've gone ahead, returning pointers from functions, returning arrays, and that sort of thing. This is where things can get tricky syntactically, because I mentioned to you, I can pass this along into a function. I set up this x, I pass it in, I create this function called print array, clear it, and return it. So I'm going to print out its value, set it to 0, and try to return it. But it's weird though. I can pass this thing in by using the square bracket notation. I can, because I was discussing, I can actually pass it along by pointer. But this is not right. I can never return an array by using the square brackets, but I can return a pointer. So what the heck? What did I do exactly wrong here? Let me rebuild this and see what the problem is. I is not a type name. What in the world? Int pointer array, int size for int I. Am I using a oh, I have a colon instead of a semicolon. Ruins your whole day, right? So, okay, so I usually use a slightly larger font as my eyes start going a little more bad every day. So here we go. From 0 to size, print, do this, and return back. And so now we have an error over here. Do we have an error over here? Too few arguments to function call. And so now, I can't pass along. I can't do this. Let me build this again. Let's see what happens once I fix this. Maybe that's just Okay. Oh, and I just need to pass the size along, which is a 10. So IntelliSense was just sitting a little behind here as to what is going on. So I go ahead here. So now let's take a look. Let's run our program. So I'm newing up memory. X is pointing to this. And what's weird about this, right, when you're newing up memory, I can't access using the debugger. All I can access is the pointer. It's not smart enough to know this thing is newed up with size 10. So at this very moment, what I need to do here is steal this guy just for a moment, just to prove that we're clearing things out and we're working with things and doing everything we're supposed to. Let me just take X here and print out X. Let's do it. Size is 10. Let me just completely disregard best practices to get this thing done. So I'll print I'll print everything out before, and then I'll add an end-line character. I will do everything in 3 places here. So there'll be 3 separate lines going on here. So I'll print out everything. So let's try it out again now that I realize I'm not going to get I can't use the debugger in a way I thought I could. So okay, so F10, and so I can go to breakpoint here and go, there's my printout. There's my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my X. And so now I can go ahead and get my new line character, go into here, print everything out, and set everything to 0. So I'm printing the 1, I'm printing the 2, I'm printing the 3, printing the 4 and the 5 and the 6 and the 7 and the 8 and the 9 and the 10. And now when I return back, print the end-line character, return back, because if I did everything correctly, X, at least I know that the first element is pointing to 0, because it did clear it out. And so now I can go ahead and print everything out, and 0, 0, 0. It seems to have worked very well here. So when I pass pointers around, I have to understand that I'm passing along memory addresses, and I'm passing along things like that. And again, that's the things I'm changing. I'm making sure that I'm changing the things I want to change and not accidentally changing things I don't. But what gets weird here, so you have to watch out for this, is local variables. So if I had something like int r equals 33 or something like that, I believe I know I could for a reference. Let me just see if I can return address of r. Let me just run this through the compiler and see what the compiler tells me. Let me build this again so I can see it. And there we go. And so it'll let me do this, and it'll let me go through and print everything out, do everything I'm supposed to. But oh my goodness, this is terrible, terrible stuff, because let's use this return value this time around. And so let's say int pointer e equals. And so what happens here is a local variable is trying to be returned. And this is a problem for pass by reference and pass by pointer. And so we haven't necessarily, so we've proven that the things return and everything works out. But let's take a look at this real quick and say what happens here is when I have a local variable, that variable is put on the stack. Global variables and all sorts of newed up memory are treated differently. There's like 3 different ways memory is treated. When there's the stack, there's the heap, and then there's like the global data segment. So at least 3 different ways memory is stored. And what happens is this local variable is put on the stack, the call time stack. Take assembly language class if you want to know every detail about that. I think it's interesting how it works. But what happens is I return the memory address of that guy, but then what happens is, the next thing that happens is when I return back, this is destroyed, right? This is unscoped. R is destroyed. And so I'm returning a pointer to a memory address that no longer truly exists in memory. And so because of that, just like anything else, the operating system could throw a fit. The program is not going to give me correct results because that piece of information has been corrupted. And so you might not, this is where I get into long discussions with students, and for a simple program, it might not cause any problems. So let me just say here, let me print out E. Let me just get rid of all this extra stuff, pass everything along, and let me just print out star E and then an end line. And what do I get out of the deal? I get the 33. And then you say, this is where the discussion comes from. You're like, oh, it works. And they go, yes, but you accidentally made it work. Because now, what if I just set up any other function? I'll just pass a, I'll just do something like here, return x is less than 0, return negative x, or return x using the ternary operator. There we go. And so what happens now if I call this function and I say int r equals absolute value of 2, and then I call star e? Why is this a problem? Oops, that meant to be a question mark, going too fast. Okay, so now what prints out for star e? It was 33 a second ago, right? Let me comment this out and run this again just to show you. It's printing the 33 we're discussing, because even though the stack unwound at that memory address, nothing's been overwritten yet. So you got lucky. But when I do anything else that affects the call stack before I use it, then garbage is going to come out of the result. And so now instead of printing 33, you get a garbage result because there was a 33 on there, but then when I called this function, the stack blew it out and replaced it with who knows what. And then when that was used up, that got put off the stack and got removed like anything else or whatever, because it's just a memory address or who knows what's stored in there. And then when I called that, it at least printed it out, but again, no good can come from this. So this is a big deal. That's why I don't know, is it giving me, that's why there was a warning. To me, there should be an error. It should absolutely be an error message. And it says, warning, returning address of local variable or temporary. Because that's exactly what's going on, that there's no guarantee when you go to use this thing that it's going to be correct. So I guess you could get away with it if you really, really, really knew what you were doing. But in all other situations, oopsie, that's a big problem. Okay, so that's that. And then notice I newed everything up, I deleted everything, everybody's happy, and that's pretty much the way to go when it comes to everything I know about basically how pointers work. So one last item, we will cover this in a later chapter or a later video when it comes to, basically we're trying to move away, programming, at least in C++, is trying to move away from raw pointers, because if you notice in almost every other programming language, Java, C#, Python, there is no concept of a pointer. You're using references. And so the idea of all of, a lot of everything is maintained automatically with garbage collection, reference counting, and so forth and so on. So to get away from using raw memory, using raw pointers that are newed up and deleted, there are constructs that are part of the standard template library that we can use so that a lot of those extra details, especially with memory leaks and those sort of things, will fall away. And so just real quick to say, the two I know of are unique pointer and, I know unique pointer and I know shared pointer. And I believe there's a weak pointer, and there's been others that have been deprecated over time. There was auto pointer and things like that. But so just a unique, shared, weak, and there was an auto pointer, but unless you have to use old software, you don't have to go into that. And again, that Jasudas book, if this is Advanced C++ course that you're watching, the Jasudas 2nd edition book goes into this. There's a whole chapter, or at least a whole section, on how to use these different pointer types, because they all have different reasons for being. Obviously, the three different things have three different ways to go about doing their job. And for right now, again, we're not going to discuss that. So that pretty much covers this chapter. Pointers, they're a big deal. We will see once we get into chapter 15, when we start using inheritance and polymorphism. Pointers are a big deal. We have to use pointers for polymorphism to work correctly with virtual functions. It's complicated, but it's just the way the language works out. So we have to make do. That's why we have to spend so much time completely understanding how a pointer is working under the hood. But as always, if you have any questions, swardb@cud.edu. Send a comment here on YouTube. Thanks for sticking it out. The next video will probably be structures, especially for the advanced students, because now that we understand pointers, now we can start moving into the baby goose steps into object-oriented programming. And those of you in other courses, I'm not sure exactly what will be next up on your agenda, but you will see it in the playlist list on YouTube there. So thank you everybody for sticking with it, and I'll see you next time.